Hi friends, I am Dr. G. Srinivasa Gupta, Professor from Mechanical Engineering Department of VJEC JYOTHI Institute of Engineering Technology. As a part of Dynamics of Machinery course, today we are going to discuss the concept on balancing of rotating masses, static and dynamic balancing. Of course, the balancing required for both rotating and reciprocating masses. First, let us see balancing of rotating masses in this lecture, both static and dynamic balancing. Why balancing needed? Basically, balancing of rotating masses ensures that centrifugal forces and moments produced by rotating parts about the rotational axis do not cause vibration or excessive bearing loads. When it causes excessive bearing loads, when the mass center of all the rotating mass is not aligning with the axis of rotation of the shaft, then there will be a mass located away from the axis of rotation. While it's in its motion, it leads to creation of centrifugal forces and moments also. So basically, the balancing of these rotating masses are in two ways we need to balance. One is static balancing and dynamic balancing. It depends on whether only forces need to be balanced or both forces and moments are balanced. Depends on case, the particular application. Sometimes, okay, if the masses are all rotating in single plane, okay, then static balance, only force balance required. If various masses are rotating in different planes, then moments also arise due to the masses about with reference to any one plane from the forces on other plane. Then dynamic balancing also required. Means static balancing means rotating system is said to be statically balanced if the center of gravity of the rotating masses lies on the axis of rotation. Balancing case, this one. In other words, the resultant centrifugal force is 0. Okay, as we know that rotors and flywheels and gears, pulleys, all these are mounted on the shaft. Okay, so when this, let us take some gear or pulley. If the mass center of this center, it has some mass, it is rotating element, it rotates along with the shaft. If the mass center is aligned, that means lies on the center of the rotation of the shaft. This is the shaft. Okay, shaft. Okay, gear or pulley or flywheel, whatever it may be. The mass center of this gear is located on the axis of the shaft or rotation of the shaft. Then there is no unbalanced forces which leads to centrifugal action. Okay, so we can say that if the mass center of the gear or whatever element which is mounted on the shaft is lying away from this, then here the mass center is located. Then with this radius of rotation, the mass having unbalanced force. Okay, so condition for static balancing, whatever number of forces, number of masses located, suppose unbalanced masses, we can take like this. This is one unbalanced mass, this is another unbalanced mass. Okay, this direction, this is another unbalanced mass. If all these are mass center of all these lying on the axis of the shaft, there is no problem. That is MR. We know that the centrifugal force we are going to write is MR omega square. Okay, so sum of this all MI, okay, R omega square, RI omega square, I, okay, 1 to n masses rotating in that. Then the sum of these, okay, must be 0. Because shaft is rotating with omega, all the masses are rotating with omega, we need not worry about omega square term. So directly we can check this product of MR sum of the product of MR is going to 0 or not. Okay, so resultant centrifugal force must be 0. This means the vector sum of the products of mass and radius must be 0. Okay, centrifugal force acting on each mass, we know that. How do we calculate is mr omega square, where m is mass, r is radius of rotation, omega is angular velocity. Okay, omega square is common for all masses, so we need not show this in this equation. Okay, I think is it very simple and easy to understand. Coming to the further explanation, if a rotor is mounted on frictionless bearing and allowed to rotate freely, okay, we know that if unbalanced, the heavy portion moves downwards, or centrifugal force it creates because of mass is away from the center of rotation. If it is balanced, it is remains in its position. Because centrifugal action, it leads to pulling the shaft. Shaft may bend. Okay, the static balancing eliminates unbalanced centrifugal forces. If it is balanced, unbalanced centrifugal forces are eliminated. So how we can make it balanced if there are any unbalanced forces are present? Then there are two methods. One is graphical method, second one is analytical method. Okay, graphical method, what we are going to do, number of forces are acting, okay, unbalanced forces in different directions. Suppose, okay, 1, 2, 3, radius of rotation, also this is R1, this is R2, from the okay, central axis, R3, okay, mass M1, M2, M3, okay. Then so how we can graphically make it balance means we need to construct a polygon. Okay, we take the mr omega square, first one m1 r1 omega square. Okay, that is the one quantity, vector quantity you have to draw. Take reference line and the inclination with the reference line, this is theta 1, let us say. This inclination is theta 2, let us say. This inclination with this is theta 3. Okay, this is minus theta 3, or you can move anti-clockwise direction. This is theta 3 like this. So first one, force mr omega square, it is the inclination with the reference line. This is first force m1 f1 mr on m1 r1 omega square. Omega we need not worry because common to all. All are attached to single shaft, and also masses are rotating in single plane. Okay, so I have taken this is x, this is y, and this is z. So masses are rotating in xy plane. I have taken. Okay, in this case. So F1. Then F2. F2 is in this direction. So head of the this F1 is here. So tail of the F2 is starting from head of the F1. Okay, this is F2. Okay, this is orientation you have seen this one theta 2. Similarly F3. F3 is located in this direction. So F3 from head of the F2 to F3. If it is forming closed polygon, then the forces are balanced. If it is not forming closed polygon, suppose it is going to this is F1, this one, F2 is this one. Suppose as per magnitude we take scale and draw exactly. Then F3 is leaving F3 is okay this much only magnitude. Okay, and direction as shown. So then this closed side represents unbalanced force which is needed to be balanced. This much force is required. This is the resultant of all these. Then opposite direction we have to attach this much force which is equal to mass, which is equivalent radius of RE. Okay, ME RE. Omega is okay. We have to calculate accordingly. We have to attach to this to make it balance. Suppose resultant, we have resultant is this one. Let us say this is the resultant is this one. So this is the resultant, this much. Then what we need to because the resultant of this this one vector F E. Okay. Then equivalent we have to attach to the shaft mass ME RE distance, okay, omega square anyhow, omega it is rotated. So this should be attached mass required, okay. So it is total, whatever masses attached, that MR, so algebraic sum of product of this MR must be 0. This is graphical method. Analytical method, what we can do, it is very simple. resolve this all the forces in x component and x direction and y direction. Suppose F1 cos theta 1 x component of F1 plus F2 okay cos theta 2 x component of F2 like that. Okay, all these you can sum it and see that it is balancing, means is equal to 0. Similarly, the other one F1 sin theta 1 plus F2 sin theta 2, F3 sin theta 3, etc. Whatever number of masses, you have to write that equation and see that summation is going to be 0. Then it is balanced. So that only given sigma means summation of mr cos theta E must be equal to 0. Summation of mr sin theta must be equal to 0. From these two equations, the balancing mass and its position can be determined. Okay, if it is not 0, then the resultant equivalent amount of force need to be attached. So what are the characteristics of static balancing? We have seen all masses lie in one plane, here one plane only. Okay, if there are different planes masses, we come to know that they require dynamic balancing. Okay, only centrifugal force is considered. Couples are not at all, there are no couples because about this central axis, because it is attached all the line of action of all forces passing through this point as an axis. So we need not worry about couples. Okay, practical examples. Grinding wheels, if there is any unbalanced mass in the entire grinding wheel, means mass center is not passing through center of axis of rotation of the shaft. Flywheels, pulleys, gears, okay, any item which is mounted on the shaft which is unbalanced, means it creates centrifugal force and we need to be taken care balancing of that. Otherwise, what is the consequence? We have seen vibration or excessive bearing loads which leads to failure of the it cannot render its function and failure is the result. Now coming to the dynamic balancing. As we have seen, a rotating system is dynamically balanced if the resultant centrifugal force is 0. That must be 0, and as well as the resultant centrifugal couple is also 0. When this couple arises, both the force balance and moment balance must be satisfied. But of course, when couple arises, when various masses are moving in different planes, suppose this is the one plane, okay, this is one plane, this is another plane. If you take this is my z axis, okay, xy, this is y, this is x, okay, xy plane, the masses are there in one plane, this is one plane, this is these two planes, this is also we can say xy plane, but these two planes are separated some distance L. Then what happened? These whatever forces are there in this plane, force 1, okay, force 1, force 2, okay, I will say like this, force 2, and in this plane also number of forces, okay, F1 1, I will write F1 2, F1 3, like these forces. Here F2 1, F2 2, F2 3, okay, number of force masses are located away from the center of rotation, different masses. Then if the mass center of all these passing through central axis, then no problem. Otherwise, there will be unbalanced force, it needs to be balanced. Apart from unbalanced force, what happened? That force leads to movement about other plane with refer to other plane. Here also suppose unbalanced force is there. This leads to movement about any other reference plane if you take. Okay, plane 1, plane 2, let us say. Any unbalanced force in plane 1 leads to movement about reference plane 2, or any unbalanced force in plane 2 leads to movement about reference plane 1. This leads to moment unbalance. Okay, so we need to see that centrifugal forces as well as couple formed due to this centrifugal force also need to be balanced. This type of balancing of both centrifugal force as well as centrifugal couple is called dynamic balancing of rotating masses. Okay, what is the condition need to be satisfied? A system is considered as dynamic balancing. Forces need to be balanced. That is, as we have seen, static balancing also forces need to be balanced. So algebraic sum of all product of masses and radius of rotation. And couple balance also, this is one, this is couple balance. Couple balance how we will write, because this is the length, whatever force, resultant force here, mr omega square into L will give moment about that force about this plane too, or vice versa. Whatever couples mr, here also omega square is need not common to all the moment terms. So this is satisfied, these two conditions if satisfied, then the then the system is called dynamically balanced. When masses are located in different axial planes only, this movement arises. Okay, their centrifugal forces form couples. Okay, even if the forces cancel, the rotor may still pull due to suppose forces. This is the resultant force, it is in this direction, resultant R1 let us say, and the resultant of all these forces in this direction FR2 let us say. Then forces are balancing, suppose magnitude also equal, resultant magnitude, forces are balancing, but this leads to formation of couple. This form couple about this plane, this form couple about this plane, so both are in same direction, so added, that couple is unbalanced. So that's why even though mass forces are balanced, the rotor may still wobble, means vibrate due to unbalanced couples. So unbalanced forces as well as unbalanced couples need to be balanced in case of dynamic balancing. So I think you are able to understand how to do dynamic balancing in case of the balancing is not already existing. In case of dynamic case, then here also we will see different approaches. Graphical method, we need to, apart from false polygon, we need to draw couple polygon also here. Then we will see whether they are forming closed polygon or not, both force polygon and couple polygon. As we have seen in case of static balance how to draw force polygon, each force we will take tail and head direction with refer to reference line. Like that couple also we need to take and draw the couple polygon. Okay, both must be closed for complete balance. This is graphical method. Coming to the empirical method, okay, here also we need to solve equations similar. Okay, sigma MRL must be 0. Okay, all take x direction and y direction, or overall we can say sigma MR equal 0, and moments, sum of the moments also must be 0. Writing corresponding equations and we can see that. Okay, and this arises in suppose dynamic balancing of missions are concerned. Modern industries are used, these are the application part. If you see computerized balancing machines, practically how it is going to be done. Computerized balancing machines, laser alignment systems, vibration analyzers, these are all attached and find these can be measured unbalancing forces or moments, and we are going to see how much mass need to be attached in what is the direction, such that in different planes in case of dynamic balancing, such that it is to be balanced. Okay, what are practical example? Automobile crankshafts are masses located in along the length of the shaft to different locations. If all the mass centers of rotation, entire mass center is not lying in one plane, any plane you take, so all the mass center is not lying on the axis of rotation, then there will be a, suppose mass center is found some distance from axis of rotation at any plane. Along the crankshaft, number of masses are located. Turbine rotors and electric motor armatures, ship propeller shafts, these are having some length and masses are located in different positions, and we need to see that whether the movements also, because these are all, these examples all create dynamic case, comes under dynamic case, and centrifugal force movements also arises. So all these movements are balancing or not, we need to check. As well as aircraft engines, these systems have masses in multiple planes and high rotational speeds. If speed is very high, then these unbalancing forces as well as couples are also magnitude reaches very peak level. These leads to bending of the shaft, heavy loads on the bearings and bending of the shaft, and failure is the result. Okay, so then if we compare these static and dynamic balancing, as we have seen, static balancing result in centrifugal force only 0. all sum of centrifugal forces must be 0. Or whatever mass is rotating on the shaft, all centrifugal forces due to these masses, algebraic sum must be 0. And in dynamic balancing, both force and moments, algebraic sum must be 0 separately. Number of planes. In one plane only masses are attached, then it comes under static balancing case. In multiple planes only, then moments will be created and it comes under multiple dynamic balancing. What are the conditions need to be satisfied? Okay, algebraic sum of all the mass into radius into omega square, of course common, so we can write mr, sigma mr is 0. In case of dynamic balancing, sigma mrl must be 0. Okay, so what we need to do to balance it if it is unbalanced? Then in static balancing, only force need to be balanced. Resultant force is exists because of all the rotational forces or masses. Then unbalanced force needs to be checked and additional mass need to be attached in the direction and magnitude we need to calculate, and radius of rotation and magnitude. And in case of dynamic balancing, we need to take care while attaching masses in different planes, unbalanced force as well as couple. Okay, complexity wise, static balancing is simple. On one plane, directly we can draw one polygon and see that unbalanced resultant is there. Then opposite to that direction, we need to attach some mass with required radius of rotation. It is simple. And dynamic balancing, we need to see also couple balancing, so a little bit more complex. So applications in static balancing only grinding wheels and pulleys, gears in one plane which they are rotating. In case of crankshaft and turbines, rotors and all these, they are having masses located in along the length of the shaft. So we need to see that movement arises due to centrifugal force created by different masses located at different planes need to be balanced. This comes under dynamic balancing. So dynamic balance automatically ensures static balance, but static balance does not guarantee dynamic balance. Why? Because dynamic balance means force and moments are taken care, balancing. Static balance only forces only, because force balance only we are going to do in static balancing. So whether dynamic balancing is there or not, by doing merely static balance is not correct. But dynamic balancing, static balance also simultaneously checked. Okay, I think you are able to understand what is the importance, engineering importance. Okay, if properly balanced all the masses, that reduce vibration, increase bearing life, prevent shaft fatigue, because shaft bends if rotating masses, shaft will bend different directions. If the mass is completely the rotating masses are reverse their position exactly opposite, then shaft will bend upward, and if it comes under mass is in upward direction, shaft will bend downward. So this is fatigue is the phenomena exist in the shaft that can be prevented if it is balanced. So efficiency of the machine obviously improved and noise will be reduced. So in conclusion, we can say static balancing eliminates resultant centrifugal force. Dynamic balance eliminates both centrifugal force and centrifugal couple. So dynamic balancing is therefore essential for high speed machinery, because very high speeds the unbalanced forces and couples dominate and which cannot be controlled. So failure is the result. So we maybe greater loss may also exist. So we need to take care. This balancing is and it is very, very important in machinery especially. So with this I am concluding this lecture here, and some numerical exercises we will attempt on these both the cases in my next lecture. Okay, we will meet then. Thank you one and all.
Like, share, comment and subscribe VNR Digital Learning Resource YouTube channel.